All right, LJ here. Let's look at some math. Well, stats in this case. So we're looking at how we can use the normal distribution to make an approximation for the binomial distribution or for the Poisson distribution. So we're dealing with random variables that have standard deviations, variances, or means, things like that. So we can actually take the information that we have in these cases and use this normal distribution to give us approximate values for them. Well, let's look and see what happens and why that's the case. It turns out that the central limit theorem has a big reason to do with why we can actually deal with this normal approximations. N is large. So a normal distribution section, but normal distribution section, we had the central limit theorem and the normal distribution as an approximation to a random variable with a large number of trials, right? So we have a normal distribution. It's almost like a superpower. It gives us the ability to approximate other distributions. Well, these two in particular. Right. So here's an example. If you were to have some rockets, you can see here that our distribution graph is there, and we could start off with having launches be a success versus they could be failing, right? So we have a binomial distribution here with success or failure, like a heads or tails situation, 14 attempts. Once we get that calculated out, you could use your binomial. This is the binomial rule here. So your n is equal to 14, or you can have up to that many trials going on, or that many successes, up to 14 successes. Like every trial could be a failure, or every trial could be a success. Right? You can calculate this way, or it turns out you can actually use this formula where you have your 1 over 2 pi, it's 1 over the square root of 2 pi, times this here at 1.87 is actually the standard deviation, or the n times the p. And we can use those to get this to approximate. Actually, it's the other way around. This to approximate this. Okay. I'll leave you to go through. The work is followed. The work is following throughout the section. Okay. A few examples through here. I'll leave those for the reader. You don't have a tighter grasp of those definitions above. All right. Normal approximation to the binomial distribution is modeled through this relationship. And say if we wanted to modify using the continuity correction, we can apply it as follows. We have these as our relationship that we like to leverage. And with our probability being taking over all of its values up to x. Then here you're going up to x plus another 0.5. Then you can have this as an approximately this value here. Now notice that this or this situation are similar, but it would look at whether or not we're going above or below our variable and having its bounds to go above x or below x. In either case, we have a situation where we have the probability in this first one of our variable being less than or equal to this relation. Yeah. Okay. Well, it's not related. This expression. And then on the other end of that, we would swap that and we'd have our z. We would have, say, the probability of this being less than our statistic is what we would get. Now, in either case, we're looking at our n times our p need to be greater than 5, and then this also needs to be greater than 5 for our approximation to hold. Okay. All for the binomial variable. This is your expected value. This is the variance. So that is effectively the formula for standardizing the random variable x. Okay. So the whole time we're going through here, we're using the normal approximation. We're using the normal distribution to approximate these binomial situations. And we can go through a few of those examples if you want to solidify that understanding. Understanding that continuity correction, because otherwise this portion here would not make sense to many. That is what we are using. And this is below the value of that is below what we're looking for here. Then that is how we write that correction. But then with this being below, yeah, like this, that's how we write that here, which is relevant since we had that question and they were asking about the continuity correction. We're using that continuity correction in order to use the normal distribution to approximate. Did we go too far? Did we go too far? Let's see, we go. When this is lower than what we're looking at here, the continuity correction, what do we have? Yeah. Okay. Here's another. We effectively take the n times the p. It gets the average, and then you get your standard deviation. Using the same formula, same formulas. What's the other variance? Here's another example where we're going through and you can get to practice with your actually utilizing those conversions. And remember, you have to make sure that those are within that range. You got to have those being bigger than 5 in order for this to make any sense. So looks like we're good to go with that 4.6.2 example. We have another example here where they're utilizing the formulas to go through and show that approximation between of the binomial using the normal. All right. Now, because we have a binomial distribution that's not symmetrical if P is near 0 or 1, that means if you have like probability is equal to 1.1 or probability is equal to 0.9, then we'd have some situations where this probability distribution would stack up over on one side because it's so likely that it'd be closer to 0, or a situation here where it stack over here to this other side because the frequency would be so much greater in that particular case. So remember, we have our binomial distribution is a satisfactory approximation to the hypergeometric distribution when n, the sample size, is small relative to big N. And this is from before in the chapter, previous section. The rule of thumb is that the binomial approximation is effective when the n over n is less than 0.1. So now we have another rule. We just went through a majority of the section looking at binomial and the normal distribution being approximate, or the normal distribution being an approximate for the binomial distribution using these relationships. You gotta have NP greater than 5. You gotta have N times 1 minus P to be larger than 5 for that relationship to hold. And then for this relationship, the hypergeometric distribution and the binomial distribution to be good approximates for one another, then you would need for this to be a true statement. You need for the little n over big N to be less than 0.1. So we have these relationships with the hypergeometric binomial and the normal distribution. And we additionally have a normal approximation for the Poisson distribution. Okay. In this case, we would use a Poisson random variable that would have, remember, the Poisson distribution, the Poisson variable has a mean and a variance that are the same. And in this case, this is approximately a standard normal random variable if we take this as our statistic, our Z statistic. Okay. All right. So remember, this is approximately the standard normal. Not necessarily approximately. It's even better than just having approximately normal, because normal would mean that we don't necessarily know the mean and the variance. But if you have a standard normal, then we know that the mean is 0 and the standard deviation for that one would be 1. The way the same correction used for the binomial distribution can be applied, so we need that lambda to be greater than 5. Okay. And the normal approximation to Poisson is an example. Again, you'd use that relationship above to establish what you would need. And typically, you'd have this probability because, you can get the exact calculation by using this relationship, by using this equation. And the computational difficulty is clear here, right? And by clear, I mean, okay, in this here and in this here, we have a factorial, and then we have a power, 1,000 to the x power, right? And we would be expected to substitute in the variable, the values from 0 to 950, initially going in the factorial, and that power function should be relatively decent to manage. But as we go on, I mean, once this number even gets to 100, 200, 300 or more, that calculation is going to get unwieldy, or at least computationally difficult. So we may want to use an approximation that will allow us to take a much simpler calculation. And using our z-statistic, we can actually find our probabilities, whether it's through a lookup table or calculator. Or if you got some really, really good arithmetic. So we have normal approximations of various discrete distributions, because the normal distribution, remember, is a continuous distribution, but binomial, the hypergeometric binomial, or the Poisson, or the negative binomial, those are discrete distributions. So the normal is even though it's a continuous distribution, can be used to represent an approximation for those discrete cases. We have more examples here. I'll leave the reader to explore. All right. The exponential distribution. The exponential distributions, that is related to the Poisson distribution. But in the view of the Poisson distribution, you may have a situation where you're defining a random variable to be the number of flaws along a copper wire. You know, a copper wire is going to have a certain length to it, and we're like, okay, you may have some imperfections or nicks or some type of imperfection that are being counted as flaws in a copper wire. And that may be necessary to account for if you're into building hardware and things of that nature. But the distance between the flaws, that's another random variable. Okay? The distance between the flaws is more so what we're looking at for the geometric distribution to come into play. So you can get information from the imperfections themselves, or you can get information about the distance between imperfections. Okay? Either way, they are in a certain sense dual to one another, intricately intertwined. Anywho, in general, let's say if you have this many flaws and this many millimeters of wire, okay, if the average is that lambda, we have a Poisson situation here, okay, then N has a Poisson distribution with mean lambda times X. Okay? And if we assume the wire is longer than the value of X, then we can have some situation like this, where we get e to the minus lambda X. So what this will give us is that probability of X being greater than that instance of Mhm. All right. Anywho, this is ultimately coming down with the derivation for how you come down to the Poisson distribution. The derivation of the distribution depends only on the assumption that the flaws follow a Poisson process, right? So that is the PDF for a geometric distribution. That's not, oh my goodness. I meant to say the exponential distribution. This is the PDF for the exponential distribution. Exponential. I said geometric. Exponential, exponential, exponential. And they depend upon a Poisson process in the background. So here we have from 0 to infinity. Okay. If you're looking at this as imperfections in the wire again, and x is equal to the distance between successive events from Poisson process with the mean number of events, lambda is greater than 0 per unit interval. And we have an exponential random variable with that as our that parameter as our with that lambda as our parameter. And this is our PDF again on that domain. Following results are easily obtained and left as an exercise, but you can find that this is the mu, and this is the mean in this case, and this is the standard deviation. I'm sorry, this is the variance. 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 You take the square root of this and you get the standard deviation, which again is going to be 1 over lambda. Interesting. Computer usage. You may have a situation where you have the logons, okay, modeled as a Poisson distribution or Poisson process with a mean of 25 logons per hour. What's the probability that there are no logons in an interval of 6 minutes? We can use this to actually calculate out that type of probability. Okay. You can follow that along at your own leisure. Okay. Modeling network logons. Yes, yes. So there are some more examples that one could follow in the book. Calculating probabilities of an exponential decay function. Suppose that this is your f of x, where your x is greater than 0, and you want your probability of x being greater than 2. Great practice. Check from earlier. And so what one could do, because we know that we are using our information about our exponential distribution. So, and keep in mind, whenever you want your probability of x being greater than 2, you'd have to take your value of this exponential, which is supposed to be x, we have x greater than 0. And with your probability, you integrate and you go, of course, from your 0 to infinity, typically, right? But if we know that we're looking at x being greater than 2, then we're really integrating from 2 to infinity. F of x dx, but our f of x in this case is e to the x. So, okay. e to the, minus x. See, which one could enjoy from the, you could definitely go through the inner workings of how to come up with that integral using your basic calculus 1 or maybe 2, depending on where you came from. But of course, whenever you have a limit of integration, when you have some negatives in there, when you have, some infinities in there, then you can actually take a limit as n approaches infinity, let's say, and then still come up with an expression that one could use to calculate the probability. All right. And we have other examples where if you, as long as you got your distribution, and they actually tell you the mean is equal to 23, so you can find something like this, even though they don't give the explicit function. We know that the exponential distribution has the same form. And as long as they give you that parameter, then you can use the rules that we've been dealing with for exponentials to come up with our necessary probability distribution function. And there we can calculate the probability distributions, the values of the probability. Another example, more examples. Mm-hmm. Okay, 4.72 here is going to illustrate what is called the lack of memory property. Exponential functions are going to, exponential random variables rather, will have this situation here. We have a lack of memory property. And what does that mean? I'm glad you asked. Whenever you have this relationship here, it turns out that if you're looking at the probability, the x is going to be less than t1 plus t2, and you know that the x is given to already be greater than t1. With this situation here, it's the same thing as you were looking at the probability of x being greater than t2. It's basically forgetting about what happened with t1, since it's already gotten past that portion, and just seeing what the t2 portion is contributing, or the x being less than t2 is contributing. Which should make sense because the x would have been given to be already larger than or greater than t1. So this is the portion that would contribute to the probability in question. Okay. We can use these exponential models to model exponential distributions to model accidents. You can have, for example, a stretch of highway modeled by Poisson process with mean number of accidents per mile, or per month rather, be your Poisson process. And if x is an exponential, that represents the time between accidents, then a month is about what we're going to say here. Then the value for this thing here is what we could look for. So what's the value of lambda for this process? Well, the mean number of accidents per month is equal to 6. Oh. What is the mean amount of time between accidents? Again, that's what you use this distribution 4. You have more examples of how to apply that exponential random variable. But continuous random variable is the time between events in a Poisson process. Okay, that's what we're looking at in that case. That's an exponential random variable. Got these distributions here, the airline gamma distributions. Okay. So you can determine probabilities using the airline, you can determine them using the gamma. Okay. Okay. So you got processor failure. That could be an example of these. And for example, you can have the exact exponential random variable describing the length until the first time you have an event obtained in a Poisson process. And then the generalization of the exponential distribution is the length until R events occurs in a Poisson process. So we can look at things like processor failure. Failures of a CPU or systems often modeled as Poisson processes. As a Poisson process. All right, typically failures are not caused by components wearing out, but by random failures of a large number of semiconductors in the units. Some of the units are that fail are immediately repaired, and yada yada yada. Failures are this amount per hour. You may look at the time until 4 failures occur in the system and determine the probability that X exceeds 40,000 hours. Is what they want to look at here. If you were given this amount per hour of failures, and we're counting until here, and we're looking at how likely is it that it's going to take at least 40,000 hours for this to happen. Okay. The number of failures, and then you got this many hours operation until 4 failures come through. Okay. And they're saying that this is going to happen if and only if the number of failures in 40,000 hours is 3 or less.
We've never had a caller. It's Nathan's now in most of it. He's not the one who tools. It's group always wants them.
Assumption. The failures follow a Poisson process implies that N has a Poisson distribution with this as our relationship with this many failures per hour. So then the likelihood or probability of our X being greater than 40,000 is going to be N less than 3. And the probability of us having less than 3 errors. So if you look at this, you have a situation where you can compare, you can have your variable where you're looking at the time that it would take before you get to that number of errors. Or you can look at it in terms of the way that the errors are counted. So we have related probability distributions that we can use to calculate that same probability. Okay. The previous example can be generalized to show that X is the time until the rth event in a Poisson process. If that's the case, then that means that our probability that our variable of interest is greater than the value that was selected for, well, that's going to take on this relationship right here. Okay. Because this It's the same thing as 1 minus that value. It's the probability function, probability density function. Okay. Oh my. Okay. What is effectively what's happening here is we're deriving the Erlang random variable. You follow through the steps, they have just going through one by one, but just showing the combinations of these various density distribution function or the features of these different types of variables. Like here in this case, this probability density function is what we call an Erlang random variable. But the Erlang random variable, right? You take R equal to 1, it's related to the exponential random variable. And in fact, it is the exponential random variable if you take R equal to 1. So the Erlang random variable is basically an extension of the exponential random variable. Or you could say the exponential random variable is a special case of the Erlang random variable. Now it's convenient to generalize this distribution. Okay. And this can assume any non-negative value. So the Erlang and some other common distributions become special cases of this generalized distribution. To accomplish this step, then we have the factorial function r minus 1 factorial, generalized to apply to any non-negative value of. Now, what that will look like is actually the definition of a whole function that is heavily used in probability. The gamma function, which once we get to the gamma distribution, will be heavily featured. All right. So keep in mind, this is finite. That the integral in this definition is finite. And integrating by parts, you can actually get this relationship here as a relationship. Okay. This result is left in the exercise. I think it's good practice to see how this equals that. Okay. This is also a true relation. Let me keep this in the same context as with factorials. Have the factorial of 0 equaling to 1. Okay. And here's our gamma distribution that I promised. And that gamma function that is actually featured within that distributions function. So we have this as a random variable, this with these parameters. Okay. Now, if R is an integer, I'm going to say X has an Erlang distribution. So really you're looking at the gamma distribution as the main character for this story. You get the gamma function that when you have R as an integer, you get the Erlang distribution. And then if R is equal to 1, then you get the exponential distribution from earlier.
Yeah.
Now, just as those other distributions have their mu, or that average, which can be calculated like this, or you get your variance that can be calculated in this manner. Okay. Here's some examples of how one could use these formulas to come up with your mean and your variance. in this case. And this case, they're actually using a genomics application where they're preparing a slab for high throughput genomics and a Poisson process with a mean of 2 hours per slide. So keep in mind, we're also dealing with these things again, and they have processes that are Poisson in nature. Again, that tends to be a common theme in this section when we're dealing with these related families of distributions. All right. So we also have another variant of the gamma distribution called the chi-square distribution, special case of gamma distribution, where the lambda in this case is going to be 1/2, and the R is equal to basically integer multiples of positive integer multiples of 1/2. So a half times 1 is 1/2. 1/2 times 2 is 1. 1/2 times 3 is 3/2. 1/2 times 4 is 4/2, or 2, and so forth and so forth. This distribution is discussed and is used extremely extensively when you're dealing with interval estimation and hypothesis testing. Okay. This is the shape, roughly speaking, of a chi-square distribution, what it looks like. So its variable, it's a distribution function. Say when you have these parameters values, or you have these parameters for the variable. So you have this n for the chi-square, you have this n for this n. They correspond to these graphs. In this case, you have n equal to 16 for chi-square distribution. And you can have your corresponding probabilities for those x values, or for your independent variables in this case. Keep in mind that this thing is never negative, right? As is the same has been the case for all of our probability distributions functions. Those values should be positive. Those are positive functions. Okay. Got more examples to practice if you should so care to give yourself a challenge. All right. So, the message and the main idea is we have that gamma random variable that generates other distributions like your Erlang distribution. The gamma, well, it is the gamma. It does help to actually formulate what a gamma random variable would be. And the chi-square distribution, actually, again, it's a special case of this gamma distribution where you have lambda equal to 1/2, and these are you have whole number multiples of 1/2, positive. So 1 times 1/2, 2 times 1/2, 3 times 1/2, 4 times 1/2, and so forth and so forth. All right. Now, Weibull distribution. This is, after completing the sections, student will be able to determine probabilities using the Weibull. Okay. So this is often used to model the time until failure of many different physical systems. Okay. The parameters in the distribution provide a great deal of flexibility to model systems in which the number of failures increases with time. Okay. So imagine something wearing away, maybe like a bridge or components within an electronic device. Weibull distribution is what we will use to figure out probabilities of events occurring. So this there we go. This piece here is the distribution function for this type of variable. In this case, we're going to have delta that be given. That's going to be positive. Beta that be given. That also be positive. This is what we call the shape parameter. This is the scale parameter. Delta is the scale parameter. Shape parameter is beta. special cases of this Weibull distribution is the Rayleigh distribution. Okay. The Rayleigh distribution. Oh, excuse me. When beta is equal to 1, we have the exponential distribution. And one could actually plug in and take this probability distribution function, plug in beta as 1, and simplify. Once you finish simplifying, you should see that you get the same result as you would an exponential distribution. Okay. If you take the Weibull random variable and we make that shape parameter equal to 2, then we have what's called the Rayleigh distribution. Here's an example. Well, not example, but these are the graphs of those, of the Weibull, and then with selected values for the delta or the beta. And we have that, in this case, that was just introduced to Rayleigh, or from earlier, the exponential. Okay. Cumulative distribution function. If you integrate that function that we had from before, if you integrate this here over all of its value, well, up until if you integrate over all its values, of course, you get 1. But if you go to an unknown x and you don't know necessarily where it's going to stop, then you actually get that function here, that CDF. Okay. Another function of x. The mean and variance are calculated in this fashion. Mean, variance. And here's some examples for how these distributions work. So the underlying distribution for this section would be the Weibull distribution. It was showing that you have special cases of the Weibull distribution whenever you have, for example, the shape parameters 2, you have the Rayleigh or Rayleigh, depending on where you're from, Rayleigh distribution. Or if you were to, we also have other cases where, again, from earlier, you had the exponential distribution. For the parameter, it's a special case of the Weibull, and that is when the parameter b is 1, you get the exponential. Okay. So the exponential is a special case of the Rayleigh, and then so it's the exponential case is the special case of exponential is the special case of the Weibull, and then so is the Rayleigh distribution. Okay. Now log normal distribution. We have another one here. Notice that you have the log or logarithm that's going to come into this normal situation. If you think about it, that's where we can actually go through the derivations of what one would do to actually come across this normal distribution, that it has a log associated. What does that even mean? Well, effectively, using the log and the normal distribution together, they come together. Okay. And it's very similar to how the normal distributions function would be. In this case, we have some other parameters that come in, and we of course we have the log function in here as well, but it's not that different from the calculations for a regular, if you will, normal variable. Just that, of course, you got the natural log in there, and you have these other parameters, though, these other numbers that are coming in here, symbols for them. In this case, well, we got the mean still. There's the mean. We got the variance. Here's the variance. And our x is coming out of an exponential situation. So this together, and how this will look is you have an exponential with respect to the w, but the w has a normal distribution. So if you think you got, okay, the function is going to be dependent upon a distribution that's normal, but then that's going to be inside of an exponential. Okay? That's where you get the log normal. And that's where this transformation comes up to going from the normal to the log normal. You're effectively putting a normal distribution through the ringer by having it be an exponential, e to the w in a certain sense, So whatever if this is a relationship, then you say x is equal to basically x is equal to x is equal to e raised to the w type situation. So we get to a point where you can actually put functions of one variable. You take that variable and you can transform it and put it in another variable. Okay. Here's some examples of how one could put that in motion. If you follow through, you should be able to see where your mean, standard deviation are used throughout that process, and be careful with your algebra, and you should come up with the probability that you're looking for. In this case, they're looking at the probability that lifetime exceeds 10,000 hours. If you're given the mean here, and then, and the standard deviation here. And you can use the formula to come up to a result that we're looking for. These are examples that you can follow through, of course. This makes more practice questions. Now we have more complex distribution here. This beta distribution. Okay. This is a continuous distribution. It's flexible but bounded over a founded range, useful for probability models. The proportion of solar radiation absorbed by our material, or the proportion of the maximum time required to complete a task in a project, are examples of continuous random variables over the time interval 0, 1. All right. And we could look at that as the minimum time or start time could be at 0. Then when you finish, that could be at 1. We could say the maximum time. Okay. So for this type of situation, we're actually going to be on that particular interval. We'd have a beta random variable. We have these parameters are positive, and we're using that gamma function again, where we have this as our probability distribution function. In some books, in some texts, they will actually take this quantity right here and turn it into the beta function. But that is really just a combination of those 3 gamma functions. Right? And under certain conditions for your alpha and your beta, we could have all these various shapes showing how these can be, for example, this when alpha is equal to 5 and beta is equal to 1, then we would have a curve that is something like this. But when alpha is equal to 0.5 and beta is equal to 0.5, say both, if they were the same, then you have this situation like this. Of alpha is 2 and beta is 5. And seeing how these parameters change the shape of the graph and how it actually gives some insight as to what's going on is critical. Again, you can find the mean and the variance of our random variable if it has a beta distribution by using these relationships, by using these equations, or those formulas. Example here, you can have a service of a constant velocity joint in an automobile requiring disassembly, boot replacement, and assembly. Suppose that the proportion of the total service time for disassembly follows a beta distribution with these parameters. What's the probability that a disassembly proportion exceeds 0.7? Okay, well, if X is the proportion of service for disassembly, okay, then this probability can be calculated going from X being greater than 0.7, we are on the interval from 0 to 1. So if X is greater than 0.7, then that means that it can only go from 0.7 to 1. And you're integrating over that probability distribution function. And once you input those parameters, you come up with that probability. Okay. All right. Another example, in a round trip commute to work, the return trip portion, X, of the total time around follows a beta distribution. And this is what we're given with those parameters. And that's our domain. In that case, we'd have this distribution. This is how the probabilities are. So with this in mind, you can actually take this and this graph, if you wanted, along with these for the mu, this is for the variance. And you should be able to answer these. Let's do this. Okay.
Just so we. How do you feel?
Now there are times where you can have the peak of the density, but and for this particular distribution, we call that the mode. That's calculated in this sort of fashion. We got alpha minus 1 over alpha plus beta minus 2. Right? This expression is useful to relate the peak of the probability density function to the parameters. Okay. Because it's like we got the alpha, you got the beta. It's like, what do those mean? Okay. All right. Suppose that the proportion of time to complete one task among several follows a beta distribution with this and this as your parameters. Well, the mode of the distribution is 1, based off of this calculation. The mean and variance can be obtained from the integrals, but you use that as an exercise. Okay, so we again have this beta random variable that's defined over that interval, generalized beta random variable W defined over this interval can be constructed from this. Okay. Here's some more examples. Okay. Now, summing this up, you have your probability distribution function, which represents the probability of x taking on a value between those two variables, between those two values, excuse me. So x in this case will be ranging from a to b. And you integrate the f of x and go from those bounds. Use the a and b as bounds for those integrals. In the next section, the moral of the story was that your probability distribution function is related to your cumulative distribution function by this relationship. All right. You take the derivative of the cumulative function to get the probability distribution function, or you can integrate the distribution function to get the cumulative distribution function. All right. To calculate the mean, you need this. You got to take the expected value. You get that variable times its PDF dx, which is very similar to the probability distribution function. Just keep in mind you have the x multiplied out here, and that's that difference. Okay. We use that for the mean. For the variance, similar type of calculation, but we have actually the x squared that be integrated in there in the same fashion that we would have had for the mean, but then we're subtracting that mean squared at the end of that for the variance. Okay. If you want the variance, if you want the standard deviation from the variance, you take the square root. For here, we have the probability density function of a continuous uniform random variable. That is what we have here. The probability density function describing a normal random variable. That is what we have here. We've also been using that to approximate your binomial and Poisson distributions, and it is integral in the log normal distribution. Okay. If x is a normal random variable, then z is a standard normal random variable. Okay. And that is what you have in this case. There is a relationship between the standard normal and a regular normal. And last but not least, but we have a probability density function for an exponential, which is a special case of some others as well. All right. For this section here, we have exercises. So feel free to go through and get some practice. The moral of the story here, of course, being that you have probability distribution functions, you got cumulative distribution functions, you got mean, you got your standard deviations, you got all those topics that just went through in that key pieces of and those key pieces of information that came before those exercises just in. Right. These key equations need to be heavily understood, and we want to also utilize them and recognize that they were in every section and build the foundation for your other information when it comes to what your probability distributions are and the type of information that you can extract from them. Remember, we're looking for things like your mean, your standard deviation, your mean, your variance, standard deviation, or probabilities, and where they are and how they're distributed. And then, of course, knowing your derivative relationships between your different functions can help to derive any needed results and not have to just commit items to memory. So these exercises are here to help to supplement what's going on with the rest of the section. It's really cool how these things are so heavily intertwined. You can have one variable type or normal random variable or one type of variable that is related to this other variable if you transform it in a type of way. And the main piece that we want to keep at top of mind is that we're looking for parts of a whole, looking to count out the portions that we're actually looking to identify out of the entire set of under consideration, or the parts of that population that we're sampling from out of the entire group of folks. So they sample over our it's not even just a sample, but the people under consideration out of the entire batch of folks that were collected to be studied, if you will, if you were dealing with people, or if there was some type of parameter, or if there was some other type of item or count you're looking for. Remember your what you want out of the total under consideration. And even with this under our naive probability, um, with that under our thoughts, undergirding our thoughts in the probability space, we're no longer just only taking one number and dividing it by another number and then coming up with, oh, that's our probability. We're able to now see, and we have all these extravagant ways of adding, integrating, subtracting, things like that, and just adding up the pieces that we want, but already having that division implicitly included by making sure that we hold to those rules that came from that summary section that basically puts everything in a nutshell to let you know, again, how to not just copy blindly, but you'll be able to see, okay, the relationships again between these various concepts and how just taking them one step at a time, it can help you to build into whatever that next piece of reasoning is to get the desired result. That desired result will give you an idea as to what it is and what type of formula that you will actually enact. If you want the standard deviation, then of course you would be providing the steps necessary or the formulas necessary to actually achieve that. But say if you didn't have the standard, if you didn't have the variance, you had to calculate it, then you wouldn't use this formula. You might use this one, which would be more involved. So understanding what the different pieces are allows us to be able to choose what sort of relationship that we use and what strategy that we would enact in order to find certain key pieces about our data that comes in, whether it's the average or how far spread it is, or even being able to determine what the shape of that data and whether or not it's uniform, whether or not it's normal, things of that nature. Anywho, I think that's enough for today. Signing out. Have a good night.